In this lesson, we're going to look at a technique that's pretty interesting because we're going to take an equation or an integral that doesn't have any trigonometry in it, and we're going to put some trigonometry in it to make it actually easier, which seems kind of counterintuitive there. You know, it seems like, why would you put trigonometry somewhere where you don't have to deal with it? Well, because we're stuck if we don't. Well, let's see how it works. So here we have an integral, the integral of the square root of 4 minus x squared. And, we want to solve this. And you might recognize this function here, the square root of 4 minus x squared. Well, if you square both sides and work with it a little bit, you get x squared plus y squared equals 4. That's just a circle, right? Now, technically, this is the positive square root, so it's just the half of a circle. All right, so we know the areas. Let's use some geometry real quickly. The area of the circle is 2 pi times 2 squared, but it's just a half circle. So what? Half times pi times 2 squared, which is just 2 pi, right? Okay, interesting. Interesting that our area has pi in it, but there's no pi at all. I mean, this is a indefinite integral, but hey, if we took this from -2 to 2, where's the pi coming from? Well, that's going to come from some trigonometry. So, well, let's think about it. Can we use u substitution? Maybe u is equal to 4 minus x squared. We could think about that. U equals 4 minus x squared. Well, if we were going to do that, then we'd need a du, which is -2x dx. And yeah, there's no other x's in there, so this just hits a wall pretty fast. So no, not going to happen. All right, so no u substitution. Integration by parts, we've learned that now. No, because there's not a product. That's not going to help us. So we need something else. All right, so we notice this expression, 4 minus x squared. All right, so anytime we've got the square root of something squared and something squared, we should be thinking about the Pythagorean theorem, okay? And Pythagorean theorems means right triangles. So let's look into this right triangle. Here's a right triangle. We've got an angle theta, we've got x and 2, and, well, what's the length of this missing side here? Okay, well, the Pythagorean theorem is useful here. We can call this maybe b or something like that. B squared plus x squared equals 2 squared. All right, and so if we solve this, we get 4 minus x squared, and we square root that. All right, well, there it is. There's our square root of 4 minus x squared. All right. So now we see a connection between this and our function up there. So let's write an equation relating some of these things. We want to relate this angle and x and 2. Well, that's can be done with some trigonometry, right? Sine equals x over 2. And now if we use this, this means that 2 times the sine of theta equals x, all right? And if we solve this for theta, we get theta is the inverse sine of x over 2. Those will be useful at different points in time here, all right? So now we have, let's think about the cosine. Well, the sine was useful. Well, what's going on with the cosine here? Okay, so the cosine of theta in this triangle is the square root of 4 minus x squared all over 2. So that leads us to say the square root of 4 minus x squared is equal to 2 cosine theta. That's going to be useful because now we have something that we can replace the square root with, okay? So we got the square root that we cannot integrate, but we have a way to replace it, okay? So now we want to use some trigonometric substitution to solve this integral, the integral of the square root of 4 minus x squared. Well, to do that, we can replace it. So we've got the integral of the square root of 4 minus x squared dx. That is the integral of 2 cosine theta. Now, I've got this dx, so I've replaced this, but I've got this dx I need to replace. So we're going to need this in terms of theta. So let's go back and let's use this function here. And let's rewrite this in terms of theta. All right? So we can say dx dt, or d theta, is the derivative of 2 sine is 2 cosine. All right? Or dx equals 2 cosine theta d theta. All right? That's going to be useful to us. So we're going to replace this dx here with 2 cosine theta d theta. All right, not too shabby. So that leaves us with the integral of, we got 2 times 2, that's 4. Maybe I'll pull that out in front. And then we have 2 ways of going about this. We have cosine squared theta, and we could use integration by parts, or we can use a power reduction formula. And let's use this. It's a little easier to use this formula. You may recognize this from pre-calculus. It goes like this: cosine squared of theta is equal to 1 plus cosine 2 theta all over 2. All right? So this is going to be handy for us because we can rewrite this as 4 times the integral of that whole thing, 1 plus cosine 2 theta all over 2 d theta. Now we don't have that exponent to deal with because we can't really deal with the cosine squared there with what we have, unless we used integration by parts. All right, so what does this mean? Well, if I pull this 1/2 out here, let's pull this out, and we'll have 4 times 1/2, so that's 2 times the integral of 1 plus cosine 2 theta d theta. And we can work with that. So we have 2. Let's integrate. Integral of 1 is theta. Plus, all right, so we're going to do a little u substitution here for this part. This is u. du is 2. I wish I had a 2 out here. So this will be 1/2. Integral of cosine is negative sine. And that'll be of 2 theta. So we did some u substitution there. You can kind of work that out slowly if you need to there. Okay. And so we have 2 theta. Just distribute here. Plus 2 times 1/2 is 1. So that's actually going to become a minus there because of the minus sign. Minus sine 2 theta. Okay. And now our goal is just to get this back into terms of x. So we can have, we got one more formula we're going to use. Sine of 2 theta is 2 times the sine times the cosine. Hopefully that rings a bell from pre-calculus. Okay. So now let's just substitute. We know what theta is. Up here, theta is the inverse sine of x over 2, right? So the inverse sine of x over 2, that's this part, minus 2 times the sine times the cosine. 2 times the sine of theta. What's the sine of theta? Well, the sine of theta is x over 2. Okay, let me go ahead and write this out. Sine theta, cosine theta. just so we keep our head on straight. Okay, and so we're almost there. 2 times the inverse sine of x over 2 minus 2 times the sine. Sorry, keep writing s instead of 2. Wrong squiggly. Okay, the sine is x over 2. And cosine is, right here, square root of 4 minus x squared all over 2. So square root of 4 minus x squared all over 2. Okay, a little bit of cleanup, and we're done. Maybe let's cancel these 2's out there. So 2 times the inverse sine of x over 2 minus x square root of 4 minus x squared all over 2. Oh boy. There it is. Okay. And that is, I'll bring this back down, the integral of 4 minus x squared dx. All right. So there you have it. So the big idea was we took that expression, changed it into terms of sine and cosines and thetas. Then we can work with it, use some trig identities, and in the end, we can know how to take the integral of some of that right here. Pretty easy integral. And then it's just a matter of getting it back into an easy form that we can work with in terms of x. All right, I mean, we could have dropped some x in here and it would have been a little ugly with all the sines and cosines. So, but this turns out to be a lot nicer there. All right. So here's the big idea. So whenever we have something like we just had, where we have a here is a constant, all right? A squared minus u squared, u is a function of x. So if we have something in this form like we just had, then we're going to want to define u as a times the sine of theta, or sine of theta is u over a. Okay? And we can work from there, and we get, the square root of a squared minus u squared, that's a times the cosine of theta. Sometimes drawing the triangle can be helpful. If we have the square root of a squared plus u squared, well, we want to use a tangent because we want u and a to be over here, so we get that line. So they're a tangent. Tangent of theta is u over a. Okay, and then the square root of a squared plus u squared, that's equal to a times the secant of theta. And then last but not least, if we want to use a u squared, or a function of x squared minus some number squared, well, that's going to be using secant of theta is a over u. And then we're going to have the square root is a tangent theta if u is bigger than a, or negative a tangent theta if u is less than negative a. Now we're just kind of going to kind of scratch the surface here, all right? So in fact, when you're doing your exercises, you won't have to guess which one to use. You'll be, many of them will just be given which one to use, all right? Well, so let's look at this here. So here we have a function of x squared plus 1. Okay, so that's in this form. So we're going to want to use u equals a tangent theta, all right? So we're going to rewrite, first of all, let's rewrite it so we can look at this. So we have 1 over the square root of, well, this is 2x squared plus 1 squared dx. So we can see that u is 2x and a is 1. And let's use u equals a tangent theta. Okay. Which means 2x equals 1 times the tangent of theta. All right. And since let's look at our right triangle here, we're using theta And we're saying u over a. And this is the square root of a squared plus u squared, or actually u squared plus a squared. Doesn't matter what order because they're adding. All right. So we have the secant of theta is going to be a over u squared plus a squared. Okay. And in this case, let's go ahead and put our number. So we said a is 1 and u is 2x. Okay. So here, secant of theta is the square root of 2x squared plus 1 squared all over 1. And that 1 doesn't need to be there, so the square root of 2x squared, also known as, I'll just write it, yeah, whatever, 2x squared plus 1 is secant theta. All right, that should do it for us. So this is the integral of 1 over secant theta. Now we need to replace our dx. Let's look at what we have here. We have some definitions here that are going to be useful to us. Really just the second one there. So we have 2x. So if we solve this, take the derivative of both sides, that is. Divide by 2 and take the derivative, that is. Derivative of tangent is secant squared. And we're going to have a 1/2 in there because we need to divide by 2. All right. So dx is 1/2 secant squared theta. So let's get that in there. So we got 1/2 secant squared theta, and that would be d theta. Okay, don't forget your d theta there. So let's clean this up and see what we can do. We got 1/2. And then we got secant squared over secant, which is secant of theta, d theta. Okay. Now the integral of secant theta we can look up on our integral tables. We had some derivative and integral tables back on some of our toolkits. But it just becomes the natural log of secant theta plus tangent theta. Okay, plus c. I think I told you I forgot my plus c on the last one. Don't forget the plus c like I did. All right, so now let's just substitute and we're done. So we have, change colors here, 1/2 times the natural log of the secant of theta. What's theta? Well, we actually don't need the secant of theta. We know what the secant of theta is right here. Square root of 2x squared plus 1, also known as the square root of 4x squared plus 1. That's secant theta. Tangent theta we know is 2x. That comes from right here. Tangent theta we know. So plus 2x plus c. Okay, there you go. All right, so we were able to do that. We convert it to trig and then back. All right, one more. So how about the square root of x squared minus 3? Excuse me. X squared minus 3, so which one is that? Okay, that falls under this guy right here. So we're going to let u equals a secant theta. All right, so u equals a secant theta. So this is the square root of x squared minus 3. That's the, that is the square root of u squared minus a squared. So u is x and a is the square root of 3. Okay, so our formula, we're going to let u secant of theta is u over a. Okay, so secant of theta is u over a. So x equals square root of 3 times the secant of theta. Now, we're going to use this top one here because we're talking about a triangle that's less than 90. Because it's a right triangle there, so we have that square root of x squared minus 3. That's going to be a, which is the square root of 3 times the tangent of theta. All right, using that thing right there up top. All right, so we should be able to do some substitution here. Let's see what we get. So this integral is equal to the integral of, so the top one there is going to be the square root of 3 times the tangent of theta. And the bottom x is the square root of 3 times the secant of theta, d theta. Oh, we need to figure out what d theta is. So we can go right here. Dx is, what do we got? Square root of 3. Derivative of secant is secant tangent. So secant theta, tangent theta. And that's d theta. All right, so let's go substitute. Going to run out of room here. All right, so we've substituted for the square root of x minus x squared minus 3. We substituted for x. We need to substitute for dx. So we have dx is the square root of 3 secant theta tangent theta, or d theta. All right. So now let's just clean that up, and we should be able to finish it off. Okay. So we'll cancel some of those out. We'll cancel the secant, and we've just got tangent squared, right? So let's take the square root of 3 out. We got 1 square root of 3 left. Tangent times tangent is tangent squared. Okay. And we're not familiar with the integral of tangent squared, but here's where we need another trig substitution. And we're going to use the fact that tangent squared is equal to secant squared theta minus 1. Remember that from pre-calculus, all right? We're pulling all these out. It's been a while. So let's rewrite it. The reason why we know that, we know how to integrate secant squared. And we know how to integrate 1. But we're not super familiar with secant, or with tangent squared, okay? So that leaves us with the square root of 3. And we integrate secant squared, we get tangent. And we integrate 1, we get theta plus c. And then, last but not least, we've got tangent theta. Well, what is tangent theta? Tangent theta, we said, was from here, we're going to get the square root of x squared minus 3 all over the square root of 3. That's what the tangent of theta is equal to, minus theta. And theta, we'll get that from this line right here. Divide by 3 and take the inverse secant. We get inverse secant of x over the square root of 3. We'll leave it at that. Beautiful, isn't it? All right. So again, the big idea is we can use these right triangles. We can change things into trig functions, do the integration, and then change it back to x in the end. All right? So this is one that takes some practice. Don't get too overwhelmed by these trig substitutions. We'll try to not wrestle with that too much, but yeah, it is useful to remember that they exist. You can look them up, all right, and just remember that this is the key right here, okay? So for these different forms, we use these substitutions, okay, and it can help to draw the triangle and get the relationships you need. So keep it up with some practice. It'll all come together.